Hey everyone, welcome to the Func Med Nation podcast. I'm your host, Dr. Steve Noseworthy. The views and opinions of guests on this podcast are their own and may differ from my own. But as always, I try to be respectful of other people's opinions, even when we might disagree. All right, guys, we're back with Dr. Nathan Bryan. This is part 2 of our discussion on nitric oxide as promised. And we were just laughing before we hit the recording button that we have an ambitious agenda. So I'm going to hope that we're going to get everything without having to push this into a part 3. In the document that I sent you with the topics of things that I wanted to go through, I did want to do just a super quick review, which might feel redundant to anybody who's listening. But to be honest, I think when I went back and I listened to that first conversation that we had, there were so many just little statements that I wanted to explore, but we kind of couldn't because I wanted to cover a certain breadth of material. And today I'd like to develop a little bit more depth. But
Sure.
Can you, super quick, and this is on the science side, and I'll throw a few things out there that you can just start to riff off and go through, and I'll kind of bring us back to the list if I need to. But I would like you to review the 2 different biochemical pathways through which we produce nitric oxide. And then, well, without throwing too many things, let's talk about some of the most common ways that nitric oxide systems become dysregulated. Because I know that you've made statements in the literature, but also in lectures that you've done, that it's very common to lose control of this system as we age. But I know that there are other things, certainly metabolic conditions can do that. So let's back up and say, hey, where do we get nitric oxide? And then let's talk about how it goes wrong. So you can take it away.
Sure. Yeah. So today, we understand there's 2 primary pathways where the human body makes nitric oxide. The first pathway to be discovered was really through the discovery of an enzyme called nitric oxide synthase. It was found primarily in our immune cells. It's how our immune system fights off invading pathogens. Then there was an isoform found in neurons called nNOS. And then there was an isoform found in the lining of the blood vessel. So now we know that these nitric oxide synthase enzymes are pretty ubiquitous in most cell types. So they're not just in endothelial cells, neuronal cells, or immune cells. They're expressed in most cell types. And this enzyme converts L-arginine, which is an amino acid, into nitric oxide. And biochemically, this is a energetically and kinetically unfavorable reaction. It's a 5-electron oxidation of L-arginine. So a lot of things have to go right for that enzyme to produce nitric oxide. And it's that enzyme that's responsible for the second-to-second regulation of blood flow, neurotransmission, and then when we get exposed to some pathogen, whether it's virus or bacteria, then there's an upregulation of the iNOS, or to help fight off the infection.
Yep.
So when the BH4 tetrahydrobiopterin, which is a critical cofactor for this 5-electron oxidation, when that molecule becomes oxidized, that leads to NOS uncoupling. So that's really the rate-limiting step in nitric oxide production.
So can you define that? Because you used the term uncoupling, and I understand certainly what it means in reference to like mitochondrial uncoupling and increased oxidative stress and lack of ATP production. When you say iNOS or you say NOS uncoupling, what do you refer to, or what are you referring to?
Well, NOS, in biochemically speaking, NOS is what's called a homodimer. So it's basically two basically identical parts of an enzyme that come together, and this allows for this flow of electrons through this enzyme that catalyzes the reaction of arginine to nitric oxide. So there has to be a flow of electrons for this reaction to occur. So when there's oxidation of BH4, there's limitation of other cofactors, then this enzyme kind of breaks apart. There's a disruption of the flow of electrons. And now, instead of producing nitric oxide, this enzyme produces superoxide.
Yeah.
Reduces molecular oxygen to superoxide. So now you have an additional source of oxidative stress. So NOS uncoupling is a major contributor to oxidative stress. So it basically exacerbates the condition. So so there are a number of things that contribute to that. It's oxidative stress. We're exposed to when you have an imbalance of antioxidants versus oxidants, we call that oxidative stress. Inflammation causes oxidative stress. If you're eating an inflammatory diet, if you get some type of chronic inflammation, that leads to oxidative stress, BH4 oxidation, NOS uncoupling. And so there's also some, genetic issues that predispose you. The methyl tetrahydrofolate reductase, SNP, which, is common, probably, depending on which study, maybe 45 to 50% of Americans have a NOS or a MTHFR SNP. Obviously, if you have a single nucleotide polymorphism in the NOS enzyme, that will lead to a dysfunctional nitric oxide production. So it's basically the Western lifestyle that leads to NOS uncoupling. It's a sedentary lifestyle, lack of exercise. It's an inflammatory diet, a lot of processed foods, simple carbohydrates, sugar, overexposure. Not only can you get NOS oxide or BH4 oxidation, but you can actually glycate the NOS enzyme. So when sugar sticks to the enzyme, it causes a disruption in its function. So just like hemoglobin A1C, where we measure the amount of sugar bound to hemoglobin, sugar sticks to a lot of enzymes, and so it can stick to the NOS enzyme and render it unfunctional. So it's really the Western lifestyle that leads to this. And the older we get, the less we make through that pathway. There's now evidence that glyphosate uncouples NOS, so that's Roundup that's sprayed on foods, other herbicides, pesticides. There's some work by Stephanie Seneff at MIT showing that 5G or certain electromagnetic radiation or certain frequencies will disrupt nitric oxide production.
Right.
So it's really, the world we live in is toxic, and it seems to everything that we're exposed to seems to disrupt nitric oxide production through that enzyme. But fortunately, the human physiology is redundant by nature, right? So if nitric oxide is this critical molecule that we think it is, then our grand designer wouldn't provide a single pathway to make this molecule. So compensatory, or just because I'd say that just because that pathway was the first to be discovered doesn't necessarily mean there's the primary pathway. Right?
Yeah, and that's a good question, because I was going to ask, like, you've just described the de novo synthesis, right, through the arginine pathways.
Right.
And last time, and this is the second pathway, which I think it sounds like you're getting into, which is the oral microbiome. Do you have a sense of which pathway is the primary pathway, and maybe as kind of thinking 2 steps down the road, like what's your take on this surging popularity of ketogenic diets and even the carnivore diet now, where you take all plants out of your diet, and save that one, but let's talk about the oral microbiome first.
Yeah, so this pathway was discovered back in the 60s and 70s. And this was discovered by cancer biologists because they were trying to figure out the mechanism of the certain oral cancers. And back then, 40, 50 years ago, it was thought that nitrate and nitrite in our diet would form nitrosamines, and some molecular weight nitrosamines would cause cancer. So these cancer biologists figured out that the body, number one, actually produces nitrate. And this was work by Steve Tannenbaum back in the 1970s. And that really changed the whole way that immunologists and cancer biologists thought about nitric oxide. So if nitrite and nitrate were toxic carcinogenic molecules, then why would the human body make these endogenously? So that was really the discovery of the nitric oxide synthase enzyme, because when you're exposed to some pathogen or lipopolysaccharide, then that led to an increase in nitrate circulating in the body. And then the nitrate that was circulating was actually concentrated in our salivary glands. Kidneys would reabsorb this. It's intentionally concentrated in our salivary glands. Now when we salivate, we secrete nitrate, and fast forward another 40 years, we know that the oral microbiome, the bacteria that live in the mouth, reduce nitrates, nitrite into nitric oxide. So if the human body is extremely resilient and smart, in fact, it's much smarter than any physician or scientist. So the human body doesn't make mistakes typically. And so when you're reabsorbing a molecule and then intentionally concentrated in our salivary glands, then it must have some important biological function. And now we know that is the case. So nitrate we get from our diet. When we eat foods, primarily green leafy vegetables, there's a transporter in the gut, the proximal gut, the duodenum, and then about 20% of that nitrate is reabsorbed. So it's taken up in the gut, it's reabsorbed in the kidneys, and then it's concentrated in our salivary glands. And the bacteria, the oral bacteria, then provide this 2-electron reduction of nitrate to nitrite, and humans do not have this enzyme. So we're 100% dependent upon the bacteria to do this kind of first metabolic activation step.
Right.
And now our saliva is enriched in nitrite. And years ago, I developed a salivary test strip that can detect this. And then when we swallow our own saliva, we get a burst of nitric oxide gas in the lumen of the stomach, provided there's stomach acid production. So now you begin to understand, okay, number one, we need enough nitrate. Number two, we need the oral bacteria to activate this inert molecule nitrate. And then we need stomach acid for the nitrite to become nitric oxide in the lumen of the stomach.
Let me just pause you there because again, I want to make this conversation a lot more clinical. So, what that brings to mind for me is the prevalence of things like H. pylori infections and hypochlorhydria
Yep.
and any infective and inflammatory process in the proximal duodenum, things like small intestinal bacterial overgrowth, which have the potential to disrupt barrier function and cause malabsorption. Now, we usually talk about the malabsorption in the context of larger micronutrients. Now, we're talking
Right.
about nitrogenous gases. So, is there any reason to think that things like H. pylori, hypochlorhydria, and SIBO could potentially change our ability to reabsorb that 20% that you're talking about?
Oh, yeah, for sure. I mean, without a doubt, the evidence is clear. So, as I mentioned earlier, that most pathogenic bacteria are sensitive to nitric oxide. Right? The nitric oxide that our immune system produces binds to the iron sulfur centers of bacteria, shuts down their respiration, and kills them. But yet, if there's no nitric oxide being produced in the stomach, then that provides an environment for H. pylori to start to replicate, cause ulcers. So H. pylori can only survive in an achlorhydric stomach, meaning that if you can't make stomach acid, it provides an
Yeah.
environment for these bacteria to grow, replicate, and cause ulcers. So now with the prevalent use of antacids, specifically proton pump inhibitors, basically causing your body to become immunocompromised, especially in the stomach from not just H. pylori, but from foodborne pathogens like, salmonella, botulism, even E. coli.
Yeah.
So it's a major problem. And then, there's, so again, that whole process, if you have, SIBO and overgrowth of the bacteria, or you have some type of gut dysfunction where the transporters aren't working, then we just basically excrete the nitrate that we're eating or consuming or making in the body.
Yeah.
And then, we lose this primarily nitric oxide producing pathway.
So, like in the functional medicine world, and there's many different ways to approach something like an H. pylori infection. And we'll leave SIBO off the table because that's such a complicated clinical problem. But a simplistic approach to something like H. pylori would be to use like betaine HCl or some similar type supplementation to acidify the stomach. Is there a role in your mind for like your nitric oxide lozenges? Because I know, and we'll end up talking about your particular products at the end of our discussion today. So well, I guess I'm jumping into it, but we'll just kind of gloss over it and we'll come back to it. You've got the lozenges and then you've got like the beetroot powder, which, I understand that there's an aspect of the gut microbiome that does the same kind of work that the oral microbiome does in this conversion of substrates into nitric oxide, but we're talking colonic environment. And if our problem is in the stomach and the antrum of the stomach and the proximal duodenum, it makes sense to me to add a nitric oxide element, but it's got to be through the mouth. It has to be.
That's right.
Unless you're going to just fill your mouth with beetroot powder and just salivate on that and swallow it, which I'm crazy enough to do that, but I'm not going to ask my clients to do that.
Yeah.
So is that a viable concept, just to add a nitric oxide element to an H. pylori protocol?
No, absolutely. It's very clear that the H. pylori are very sensitive to nitric oxide. If you generate nitric oxide in the environment where H. pylori is, then it kills the bacteria.
Yeah.
So yeah, it's certainly a viable. And then here's the issue, and this, if we try to give the human body kind of precursors and substrates and allow the body to do it, most of the time, especially people that are sick, they've lost the fundamental principles of how to convert these substrates into nitric oxide specifically.
Yeah.
So we have to do it for you. If your body can't make nitric oxide, then we do it for you. And that's the basis of my 20 years of research and innovation and really product development. Because if you rely on the human body to do it, then typically the basis of the underlying illness in patients is that they can't do it. And that's the reason they're nitric oxide deficient. So in terms of stomach acid, yeah, things like betaine hydrochloride are essential. But here's the issue. The parietal cells are the cells in the stomach that make hydrochloric acid. So we have to understand the chemistry of that reaction. And for the parietal cells to make hydrochloric acid in the stomach, you need several things. There's certain components in this chemical reaction. So number one, you need iodine. Number two, you need B vitamins. Number three, you need zinc. You need betaine hydrochloride. And then you need sodium bicarb. And so that's the reaction kind of that occurs. And if you can't make stomach acid, but you don't absorb B vitamins, you don't absorb iodine, you don't absorb zinc, and you become deficient in sodium bicarb secretion by the pancreas. So taking a proton pump inhibitor or an acid basically leads to nutrient deficiencies. And
Yeah.
it's not just nutrients that are needed to produce hydrochloric acid by the parietal cells, but it's things like iron and iodine and selenium and chromium and all these essential trace minerals that require stomach acid to be absorbed in the lumen of the stomach. So now we have to give the body what it needs to fuel that reaction. So 95% of Americans are deficient in iodine. So we have to supplement iodine. We need zinc, B vitamins. And so these are the things that we have to supplement then if you've been on antacids or you have achlorhydria for other reasons. Now the body has what it needs for the parietal cells to produce hydrochloric acid.
So, and this is a little bit of an aside, but I'm bringing it up just because you mentioned it, and it's been something that I've been trying to figure out myself. There's even lay people will use like sodium bicarb, like Arm & Hammer baking soda to relieve gastric upset and reflux and this kind of stuff. And we know we produce it. We know it's part of that entire process. It's a key aspect of bile acid formation and secretion, all this kind of stuff. Do you, and I know that you're not a clinician, but you know an awful lot more about biochemistry than most of us do as practitioners. From a biochemical standpoint, do you have any problem with either lay people on their own or practitioners having people use something like sodium bicarbonate as part of a strategy? Because the thought would be, well, if you take bicarb, you're just neutralizing your hydrochloric acid.
Well, no, I think it's a viable strategy. So the body always has a way of neutralizing either a strong acid or a strong base. The original kind of rationale for giving, an alkaline agent like sodium bicarb or alkaline water was to promote the parietal cells in the stomach to produce nitric oxide. Because the stomach is designed to be a pH of, less than 2 or 2 to 3. Yep. And so if you give a strong base like sodium bicarb, then that increases the pH of the stomach and it tells the stomach, hey, I need to make more hydrochloric acid. But if you're on a proton pump inhibitor or an antacid that prevents the parietal cells from making hydrochloric acid, then it's kind of, you may be doing more harm than good, because now you're raising the pH. And here's the deal. Total body pH is regulated by sodium bicarb secretion in the pancreas.
Right.
And the signal comes from the acid load from gastric emptying, right? So when there's a certain period of time that the food you eat stays in the stomach, once it's broken down, then the sphincter releases, you release the contents of the stomach into the duodenum. And that's where the sensors from the pancreas, the bile duct, and all that sense this. And once you get that sudden drop in pH in the duodenum, that tells the pancreas, hey, I need to buffer this acid. And then you get bicarb secretion. And it's that sodium bicarb secretion by the pancreas that really leads to total body pH regulation. And we know that chronic disease occurs when there's low pH, low oxygen, low voltage. And all of that is regulated by this acid dump in the stomach. So if the body doesn't sense that, then there's no secretion of bicarb. You can get, dysregulation of bile. You can get gallstones, bile stain, and it leads to complete total body dysregulation. So everything we do in the body, from the breakdown of proteins into amino acids to nutrient absorption to control of total body pH, is all determined or all predicated on the fact that the stomach can make stomach acid. So intentionally inhibiting stomach acid production is probably the worst thing we could do for our body.
But you wouldn't put an oral supplement of bicarb in the same categories of PPI, right?
No, certainly not. I mean, the body always adjusts, right? And so most drugs are inhibitors of biochemical reactions.
Yeah.
Right. And so when we give drugs, whether it's a PPI or a statin, all of these drugs are designed to inhibit a specific biochemical reaction. And when you do that, there's always consequences, because now the body can't respond to normal stimuli as it would. And that's how the body regulates. You have to give the body what it needs, get out of its way, and let the body do its job.
Yeah. Yeah. Well, that's what I call a fruitful bunny trail, but we'll leave it there and come back to the nitric oxide.
Well, that's a course.
Yes. So we've touched on it a couple of times, and that's the age-related decline of nitric oxide output. Like, at what do we lose nitric oxide output in some kind of a predictable fashion, or is it? I mean, these things are always individual dependent, but if we look across large populations, what kind of rate of decline, when does it start, and when does it accelerate?
Yes, there's typically, and when you look at, and you make a good point, so everybody's different, right? It's personalized, individualized medicine. But when we do clinical trials or clinical studies, we take a group of populations. So we select certain people. So in these studies where you look at kind of the age-dependent production of nitric oxide, we see about a 10 to 12% reduction or decline in what we call endothelial function or nitric oxide production per decade. So this can start in the late teens, early 20s, and then a 10 to 12% stepwise reduction per decade. So by the time we're 40 or 50, we've lost 50% of the nitric oxide. Then by the time you're 70 or 80, you've lost probably 85, 95% of the nitric oxide you had when you were younger. And now we know that it's that loss of nitric oxide that's responsible for age-related disease. But you can take individuals. So if you select out of there, and I'm always the N=1 experiment or the guinea pig when I take on any new project, try to figure out, okay, what's happening in me, and then try to compare this to other people. So our whole thought process more than 20 years ago, when I first started our research program, was, can we prevent this age-related decline in nitric oxide production? And if so, can we prevent age-related disease? And the answer is yes. So this isn't kind of predetermined. Now we know that we have 18, 25-year-old kids that have the vascular age or the nitric oxide production output of a 60 or 70-year-old.
Mm.
I'll be 50 next month, but I have the nitric oxide production or the biological age of a 35-year-old.
Nice.
So we know we can shift this curve to the left and to the right, and we understand the enzymology and biochemistry today to the extent that we can prevent NOS uncoupling, prevent the age-related decline in nitric oxide production. And if we do that, we prevent age-related disease.
So you said, in talking about your own personal levels, are you doing that with the salivary test strips, or how are you gauging that?
There's different ways now we can measure kind of our biological age rather than and compare it to our chronological age. I like these functional tests, and the one that we use is the EndoPad, and there's some other non-invasive devices. But what this device does is it basically, and now there's hundreds of thousands, if not millions of patients in the database, we can create an algorithm that really provides some biological age based on different outputs. So what this device does is it basically measures your ability of the blood vessels to make nitric oxide. Then you compare that to the general population, and then figure out kind of what your biological age is. There's other ways to do it. You can look at histone modification. There's many of these empirical measures of biological age, but I like the functional test. A functional test is always better than a biochemical test.
Yeah, I'll ask you if you don't mind to give me links to that. We'll put them in the episode description so we can give people some other places to go towards. So do you think it's the environmental and dietary changes, that just the accumulation of environmental insults over time, that leads to the age-related decline? Or is there, some level of senescence built into the system?
I think it's probably a little bit of both. I mean, there's not really a single cause of NOS uncoupling and loss of nitric oxide. I think primarily, just generally speaking, it's diet and lifestyle. So moderate physical exercise is known to stimulate or activate nitric oxide production. Yeah. An inflammatory diet can prevent oxidative stress, prevent BH4 oxidation, prevent NOS uncoupling. The food we eat today is deficient in most nutrients. There's, herbicides, pesticides on the food we eat. So nutrient deficiency, exposure to toxins, and lifestyle really, I think, can probably explain the NOS uncoupling in the majority of the population.
Yeah, I think we're kind of at the point where that short list of usual culprits can explain pretty much everything.
That's right.
Yeah, for sure. You had mentioned something in our last conversation about feedback inhibition when your INOS system gets... Now, look, actually, let me back up. My understanding is that the nitric oxide being produced by the INOS pathway, especially when it's upregulated in the context of infection or inflammation, is much more... it's higher than what we see coming out of the endothelial neuronal systems. Right. And I would like to ask a question down the road about cytotoxicity, but you said, when INOS gets too high, there's an autoregulatory process. Is that reflex inhibition just of the INOS pathway, or is that reflex inhibition when INOS production gets too high, all systems go down?
Yeah, no, there's always, endogenous regulation of all enzyme systems, right? So the body senses when it's made enough, shuts it down, and then it regulates it. So the INOS only occurs when there's an exposure to some inflammatory stimulus, and that can come from an infection, it can come from an injury or a wound. So then, you get this cytokine storm. We heard a lot about this during COVID. Sure. It's those cytokines that lead to an upregulation of INOS, and then the immune system then targets wherever the infection is or whether the injury is, and we create this acute inflammatory response. So there's a reason the body does this, because if there's an infection, the immune cells go there and it wants to isolate the infection so it doesn't spread.
Yep.
So it's the inflammatory response. It's the heat. It's the fever, the infection, and basically all the hallmarks of acute inflammation.
Right.
But then what happens is the nitric oxide that's produced, and you made a good point, this is about 1,000 or 10,000 times more nitric oxide, the flux of nitric oxide coming out of that enzyme, than what would be normally produced in the lining of the blood vessel or in our neurons. So inducible versus constitutive isoforms. It's a difference in the flux of nitric oxide. So when nitric oxide is produced, it forms a lot of these other nitrogen oxides, and then it can go back and actually post-translationally modify the enzyme to shut down its production. So it's self-regulating. And it's very important because acute inflammation is absolutely essential for the survival of the host, the human. But when we have chronic inflammation and we lose regulation of this, then it causes damage, collateral damage. So we published, I believe it was in 2004, for the first time showing that if you have acute overexpression or chronic overexpression of the INOS enzyme, and the model we used was inflammatory bowel disease and ulcerative colitis, which is inflammation of the gut, a chronic inflammation of the gut, where you have chronic overexpression of INOS, you're generating a lot of nitric oxide because there's some way you've lost control of regulation. But we also find that overproduction of nitric oxide in the gut can feedback inhibit the nitric oxide enzyme that's found in the lining of the blood vessels and the enzyme that's found in our brain. So this leads to vascular dysfunction. So chronically inflamed patients, even though you may see an acute or a overproduction of nitric oxide, and that's where there's a complete misinterpretation of the data in the literature. But these chronically inflamed patients, when you look in the gut, they have overproduction of nitric oxide. So people think, oh, well, nitric oxide is contributing to the pathology. But yet systemically, they're completely devoid of any nitric oxide because of the feedback inhibition and the loss of NO production in the lining of the blood vessel. So now when you have a chronically inflamed person, you shut down nitric oxide production, you lose the regulation of blood flow, and you exacerbate the inflammation, oxidative stress, and immune dysfunction. And that's why chronic inflammation without restoring the production of nitric oxide is almost impossible to overcome. And I think that to me explains why people who have autoimmune disease, chronic inflammation, it's a poorly managed disease by conventional medicine.
Yeah.
Because clinicians don't understand the basic biochemistry and the loss of regulation of nitric oxide production. And just like the same kind of phenomenon with reflux, physicians thought years ago, or scientists, that if you have reflux, it's overproduction of acid. Actually, it's insufficient stomach acid production. So they give an acid blocker, right? It's counterintuitive. So the same thing is that people think, well, when in ulcerative colitis or ALS or any type of autoimmune disease or chronic inflammatory condition, there's always nitric oxide present at the site of inflammation. So then many investigators will go, oh, well, nitric oxide is there, so nitric oxide must be contributing to the pathology, so nitric oxide's bad.
Right.
An example I like to use is, well, if you have a robbery or some crime, then the police always show up. Typically,
Yep.
I mean, we hope, right? Some cities don't want the police to show up, but that's another topic. But the police always show up at a crime scene, but the police didn't cause the crime. They're there to kind of control the environment and prevent other damage from happening. So that's what nitric oxide does in chronic inflammation. It always shows up. That's its job. So just because it's there doesn't mean that it contributes to the pathology. It's trying to rein in everything and get control of the situation. So nitric oxide and chronic inflammatory disease, you'll read a number of papers, and there's people out there that say nitric oxide's bad for you. It should be inhibited. But that's not the case at all. It's a complete misinterpretation of the data.
Yeah. So I know that you mentioned in our first conversation that this is why people with sepsis die, organ failure, because they can't perfuse the tissues, which makes complete sense. So let me toss out a clinical scenario, because we have, most of us in functional medicine these days are dealing with clients who have what I call multiple symptoms and multiple systems. And the vast majority of those are in the world of autoimmunity, some progression, and certainly some autoimmune pathologies are more difficult to manage than others. For example, things like lupus and Sjogren's, much harder to get a handle on than something like, say, Hashimoto's. But let's just use Hashimoto's because it's the most common autoimmunity and it's what most of us are dealing with on a routine basis. Generally, you have, like, there's kind of a spectrum, right? You have people who have Hashimoto's, but for whatever reason, their immune system is relatively quiet. They might flare up periodically, but they're not flared up severely or for a prolonged period of time. But on the other end of the spectrum, you have people who seem to be flared up all the time. And then you have all the different stops in between. So what about, and I'm just trying to get a handle on this excessive production of nitric oxide and the feedback inhibition, how that plays a role in a person who has some level of more than average inflammation because they have an autoimmunity. By definition, they're probably more inflamed. But then they have some frequency of flare-up episodes where they get a surge of inflammation from some trigger, known or unknown. And that inflammatory surge may last hours to days to weeks, depending on the individual person. So is it when these flare-ups resolve? I mean, sometimes it's just because you stop whatever trigger. Like I started eating gluten again and I stopped and now my inflammation goes down. But sometimes the trigger is unknown. You can't see it. You can't put your finger on it. Do you think that some of the resolution of these flare-ups is this feedback inhibition? Rather than the person who's chronically severely inflamed, it's the one who's episodically inflamed. How does nitric oxide play a role either in the initiation, response to, or resolution of that inflammatory episode?
Well, again, the body always responds. But and for me, I think what I've learned in 25 years of academia and research is that chronic disease is caused by two things and two things only. It's your body's missing something that it needs or it's exposed to something that it doesn't need.
Right.
So in chronically inflamed people, you've got to really dig a little bit deeper and figure out, okay, if the body always responds, it doesn't make mistakes, then what is the body missing, right? And then number two, even if you give the body what it needs, if it's exposed to some toxicant, whether it's environmental or some virus, and latent virus that becomes active or some, bacterial infection, the body can't do what it's designed to do. So we have to eliminate the toxins and then supplement and basically replete any missing nutrients.
Right.
And so that to me is, and the basis for autoimmunity really starts at the level of stomach acid production. Because what happens is when you can't break down proteins into amino acids, which is the job of the stomach, specifically the stomach, you need a really acidic environment for trypsin to work, for these enzymes in the stomach to break down proteins into amino acids. So the human body is never designed to incorporate plant proteins or animal proteins into human proteins, right? The reason we eat proteins is because the stomach can break it into the constituent amino acids. Then the human can assemble these amino acids into human proteins, not cow proteins or plant proteins.
Right.
When we can't break down proteins into amino acids, now we got peptide fragments, partial proteins that are released into the gut, and then you start to develop leaky gut, and then these peptide fragments are absorbed across the gut. Our immune system recognizes them as an invader, a pathogen. We start making antibodies against it, and depending upon which antibody you're looking at, you're diagnosed with lupus, Hashimoto's, thyroiditis, or whatever else. But this wouldn't happen because the body doesn't make antibodies against basic essential amino acids needed to make human proteins.
Right.
Everything we do, everything in terms of autoimmunity is related to you got to get rid of the toxin. What is the toxin? Well, it could be a peptide fragment that the human body doesn't recognize as self because the stomach can't break it down into amino acids. So we develop an immune response to it. And now we've lost regulation to the acute inflammatory response because now every time we eat, we get flu-like symptoms. We developed an inflammatory insult. This is ongoing because most people eat. I heard a story the other day that the average American eats about 23 times a day. I mean, to me, that's mind-blowing.
You glitched. Your audio glitched. Can you say that one more time?
I heard a podcast the other day, and I don't have a reference for it, but someone mentioned that the average American eats 23 times a day. And think about this. So if we can't break down, and there's proteins in a lot of the food we eat. So if we can't break down proteins and we're eating almost every hour, then we're giving our body an inflammatory insult every hour. So no wonder.
Just on a basis. Yeah.
Yeah.
Yeah, for sure. Yeah, that's another bunny trail we can go down. It's just the whole autoimmunity. Yeah, let's move on. Gosh, you've already burned 35 minutes.
Time flies.
So, No, this is wonderful because I love the depth and I love the detail. And like I said, like, the group that I lecture for in functional medicine, I believe, and it might be different now, but I think historically we've gone more into biochemistry and understanding mechanisms than any other functional medicine education group. But I think that's kind of changing because everyone's cluing in. Like, if you're a clinician, you have to understand biochemistry, especially if you're working with complicated cases.
Yeah, no, look, I mean, that's the problem with medical schools. I taught in medical school and taught future physicians for 10 or 12 years when I was on faculty at UT Medical School.
Yeah.
And here's the problem. We teach physiology and biochemistry the first year. Second year, you learn pharmacology. And then from then on, you're doing rotations and learning about insurance and coding and billing and the financial model of medicine. So most allopathic physicians, medical doctors, don't even give any consideration to the basic biochemistry and physiology they learned in medical school.
Yeah.
Because the financial model of medicine is, in order for me to get paid, I've got to make a diagnosis and code it. And then once I make a diagnosis, the standard of care only allows me a finite kind of options in terms of treatment. And it's always, how do I prescribe a drug to treat this symptom?
Right.
It's never getting to the root cause of the dysregulation of some biochemical reaction
Yeah.
or understanding the physiological systems of heart disease, or it's a problem. I think that's where you guys do the best and really make the greatest impact in patient care is you have to get to the root cause of the symptoms and not you treat the patient, not the symptom. That's the whole basis of functional medicine.
Totally agreed. You're preaching to the choir on that one.
Yeah.
And I will say that in the world of natural medicine, whether you're chiropractor, naturopath, oriental medical doctor, the lack of emphasis on biochemistry it's just as absent in that field as it is in the conventional field. And this is part of what we try to fix when we do our seminars. Again, completely different topic. So let's do. I sent you a question. I said, can we dispel a myth? And I posed it in the form of a question, and that is, can we ever eat enough hot dogs and eat enough barbecue and deli meat to cause cancer? Because that's the whole, the fear of nitrites and nitrates. And, of course, savvy marketing executives in companies that make these meat-based products say, no, nitrate and nitrite free. So can we ever eat enough to really make a difference? And if not, why not?
Now, this whole science started in the 50s and 60s where, nutritional epidemiologists were trying to create associations between the consumption of certain foods and the increased risk of certain cancers, for example, in nutritional epidemiology. And they found, even years ago that people who eat more cured and processed meats, bacon, hot dogs have it's a very slight increased risk of certain gastrointestinal cancers, whether it's stomach cancer or colon cancer. So these are associations, right? It's not causation. In order to establish causation, you have to have some biologically plausible mechanism of how this association biochemically could lead to causation. So in the 50s and 60s, they thought, oh, well, it must be the nitrite and nitrate in the cured and processed meats that cause nitrosamines. And nitrosamines at that time were known to be, some of them, carcinogenic and mutagenic to lead to cancers. So for them, the story was complete. Nitrite causes nitrosamines, it forms nitrosamines, causes cancer. That way, those people who eat cured and processed meats have a higher incidence of certain cancers. Well, fast forward, and the discovery of nitric oxide in the body actually produces nitrite and nitrate from the oxidation of nitric oxide, then the story falls apart. And then fast forward another 10, 15 years, and we know that 85% of the nitrate and nitrite that we get from our diet comes from eating green leafy vegetables,
right,
not cured and processed meats. So if their whole hypothesis was correct, vegans and people who practice a plant-based diet would have a 10-time higher rate of cancer than meat eaters. And we know it's just the opposite.
Right.
So 85% of the nitrate we get from the diet comes from eating vegetables. 5%, less than 5%, comes from eating cured and processed meats. And the other 10% comes from swallowing our own saliva. So the whole, and in fact, so to answer your question, we cannot eat enough hot dogs and bacon to get enough nitrite and nitrate to fuel a nitric oxide production pathway. In fact, since 1972, the Code of Federal Regulation changed to where they said any meat product that you add nitrite to, you must add a certain excess of vitamin C or ascorbic acid. Now, today, they use erythrobate, right? So in the hot dog, anything where sodium nitrite's added, by law, by the Code of Federal Regulation by the U.S. government, you must add erythrobate. And the reason for that was that they thought, okay, if there are secondary amines present in the food, this would inhibit any nitrosative chemistry, prevent nitrosamine formation, either preformed nitrosamines or during the cooking process. So there's number one, there's no nitrosamines in cured and processed meats. Number two, there's hardly any detectable nitrite or nitrate in cured and meat products. We published this, I believe, in 2015. So you cannot eat enough. Cured and processed meats is not a major source of nitrite and nitrate. And interestingly, in 2009, we published that these no nitrite cured bacon and hot dogs have 5 times more nitrite than So, and I've consulted for Kraft Oscar Mayer, and I've told them, I said, look, you guys shouldn't be running away from nitrite. You should be
promoting it,
fortified with nitrite. Now, these are considered indispensable nutrients that we need more of, that Americans are deficient. So here's what they do, and it's really deceptive marketing. But it's these big meat companies that are giving in to the misinformation and the demands based on ignorance by consumers. So rather than adding a sodium nitrite to cure the meat, they add celery salt, which is primarily nitrate. Then they add a culture of Staph carnosus, these nitrate-reducing bacteria. So the bacteria are converting the nitrate in the celery to nitrite. The nitrite is actually curing the meat indirectly, but because they're not adding sodium nitrite to the product, they can say no nitrite added.
Wow.
But yet the variability of these bacteria, it's wide. And so these meat products are actually, it's not a good product, because we don't know how efficient that product is. Plus, you've got residual Staph carnosus bacteria on these meat products. I tell people all the time, save your money. Don't spend the extra $1, $2, $3 a pound on the no nitrite cured. You need that nitrite in that meat. Because then if it prevents H. pylori overgrowth, it prevents botulism toxin, it prevents salmonella. There is no substitute for sodium nitrite in the meat curing industry.
So we're gonna start a new movement. Is it bring back bacon and eggs for breakfast?
No, that's right.
So I remember listening to one of your lectures where you talked about the average daily intake of nitrates and nitrites in North America and the level of toxicity required to actually be a problem. Do you remember those numbers off the top of your head?
Yeah, so we tried to quantify this, and there's certain steps. So we know that we need, in order to get this nitric oxide production pathway from the diet that we talked about earlier, we must consume enough nitrate. It must be absorbed. We must have the right bacteria to reduce it to nitrite and nitric oxide. So in an ideal scenario where we have good gut function, everything's absorbed, the transporters are working, we have the right oral bacteria, we have sufficient stomach acid production. The published literature tells us that we need 300 to 400 milligrams of nitrate in a single meal, right? Because there's inherent inefficiencies in this process. 20% of the nitrate is absorbed, and only 25% of the nitrite or nitrate that's secreted in our salivary glands is reduced to nitrite. So overall, we're only getting about 5% reduction efficacy. 20% absorbed, 25% reduced, 25% of 20% is 5%. So the standard American diet, and we quantified this, you're only getting 150 milligrams throughout the day.
That's not much.
No, it's not. So we're deficient in nitrate. Then the other problem is that 2 out of 3 Americans wake up every morning and use mouthwash, killing the microbiome. So we lose the reduction efficacy, and then we just sweat or poop out the nitrate or urinate. And then the other problem is there's 200 million prescriptions written for antacids every year, shutting down stomach acid production. And that's not even counting the over-the-counter purchases. Now you can get Prilosec, Prevacid, OTC, and people take this every day for 5, 10, 15 years, and it's killing people. Now, in 2015, it was reported that people who have been on PPIs for 3 to 5 years had a 40% higher incidence of heart attack and stroke. This last month, a new study came out. People who have been on PPIs for 3 years had a 35% increase in dementia. I mean, these drugs are killing people left and right. It's not an increased risk. It's actual events. 40% increase in heart attack and stroke, and the mechanism is clear.
You're talking about hard endpoints, not relative risk.
Yeah. These drugs are deadly, and they're killing people. And just like the Vioxx and Celebrex from the early 2000s, there should be a black box warning on all antacids, specifically PPIs. They should be taken off the market. They're killing people. The mechanism is very clear. They're shutting down nitric oxide production, causing increased risk of plaque instability, plaque rupture, decreasing blood flow to the brain, causing vascular dementia, Alzheimer's. Mechanism is very clear. These are very dangerous drugs and should not be taken.
Yeah, and I do want to talk about the whole link with plaque and plaque regression with the use of nitric oxide supplementation. Let's pause that for a second. One more point of clarification based on our conversation the first time was you made it very clear that a lack of arginine is not the reason why people don't make nitric oxide, right? It's predominantly the for insufficiency for, several different reasons. So I pose the question, why is it then that people who take, whether it's citrulline or arginine or some combination, why do they claim, well, I'm getting benefit? And you said, well, it's probably because arginine does a whole bunch of other different things. Totally get that. I was preparing this morning, I had another thought, which I shot it to you in the notes about what I wanted to talk about, but let me just kind of get it out there for people who are listening. Like arginine is a non-essential amino acid, right? We don't have to get it from our diet, but obviously we get more arginine in our bodies if we're eating a protein heavy, whether that's animal protein or whether it's plant-based protein. So could it be that people who are protein deficient and theoretically their arginine levels might be suboptimal, could it be that's why some people, like it's still a nitric oxide effect, but if someone's protein deficient, they don't have an arginine pool sufficient from which to derive nitric oxide, could they be compensating just by taking arginine where if all they did was eat more protein, they could get to the same place? And again, I'm just like riffing off the top of my head. I have no idea if it's rational or reasonable.
No, I don't think that's the case because arginine is a semi-essential amino acid, which means we get part of it from our diet, but the body makes arginine on its own. So even if we don't get arginine from the breakdown of protein, every cell has what's called a partial urea cycle, and arginine is produced from the urea cycle. Right. And so even through this pathway, intracellular levels of arginine are usually between 100 and 200 micromole. The amount of arginine in the cell that's required to theoretically saturate the binding site to make nitric oxide is only 5 micromole.
Gotcha.
What the cell makes on its own through the urea cycle is 20 to 40 times excess of what's needed to bind the enzyme to make nitric oxide. So again, unless you have some inborn error metabolism and a urea cycle disorder, you're never deficient in arginine.
Understood.
Your body makes what it needs to do its job.
And that's the same argument or concept of glutathione, right? In terms of nitric oxide and its endocrine functionality, you're always going to have enough reduced glutathione on board to bind to to bind to nitric oxide to allow it to go from one place to another, which brings up a question I had in my mind 15 minutes ago as we were talking. Is like, we were talking about people who have these autoimmune flare-ups, right? And, I would imagine that in many cases, people with targeted autoimmunities, they have antibodies to a specific tissue. We'll use the thyroid as an example again. So let's say I have Hashimoto's and I get a flare up, I'm going to have predominantly a localized inflammatory surge in thyroid tissue because that's where the immune system is being called to. And theoretically, I'll have an increase in iNOS expression in the local organ environment. Theoretically, if I have enough reduced glutathione on board, whether through endogenous production or supplementation with N-acetylcysteine or directly with acetylated glutathione, is it possible for the iNOS upregulation locally in the thyroid then to be bound by sufficient levels of glutathione, which essentially could blunt the inflammatory response and allow nitric oxide to travel to distal sites and then have an endocrine function and be beneficial to my heart or to my brain? Is that biochemically feasible?
No, absolutely. In 2007, we were the first group to publish that nitric oxide is a hormone, meaning that when it's produced in one tissue, it can be transported to other tissues and elicit the cytoprotective effects. And part of the endocrine function of nitric oxide is binding to glutathione.
Yeah.
So we have millimolar concentrations of glutathione. We only make picomolar, nanomolar concentrations of NO. So there's always excess. We're never deficient in glutathione in terms of mediating the carrier function or transport function of nitric oxide. But here's the deal. When you have inflammation, chronic inflammation, part of the inflammatory response is to generate oxidative stress, right? Because oxidative stress is part of the immune response. It's the oxidative therapy, right? It's why ozone treatment works. It's why hydrogen peroxide works, because it's oxidative therapy. But and we look at reduction oxidation, right? So as a biochemist, we count electrons, right? So reduction is when a molecule gains an electron. Oxidation is when a molecule loses an electron.
Right.
So when a molecule becomes oxidized, we have to reduce it. And the main antioxidant in the human body is glutathione. So it donates electrons and now leads to a reduction of a molecule that was oxidized. And in human physiology, it's redox balance. It's the balance of reductants versus oxidants come together that provide homeostasis. When we have an imbalance in oxidants versus reductants, then we develop pathology. So yeah, if we, again, and it goes back to the whole concept, if we give the body what it needs, the body heals itself. We need reduced glutathione. We need to be able to make nitric oxide. But understanding the biochemistry and the chemical reactions and the products needed to do this chemistry, if the body's missing it, then it can do its job.
Yeah. And so even again, I'm trying to get a sense of how to translate this clinically. So even in the context of someone who has chronic inflammatory problems, and perhaps from a laboratory standpoint, their reduced glutathione is too low, or the ratio between reduced and oxidized is too high, or I'm sorry, too low. We still, because there's such a difference in the amount of glutathione on board compared to nitric oxide production, even in glutathione deficient state globally, we still have enough available in local tissue that we're going to have some type of cytoprotection. Would that be an accurate way to state it?
Well, not necessarily, because there's what's called redox coupling, right? So when glutathione becomes oxidized, it has to be re-reduced to reduce glutathione. There's an enzyme called glutathione reductase. It's a seleno enzyme. Deficient in selenium, then we can't re-reduce glutathione or oxidize glutathione to reduce glutathione. That ties into an NADPH reductase, and then vitamin C. So there has to be a flow of electrons to lead to a reduction, because if reduction is a gain of electrons, then we have to have electron donors to reduce things. And if we're under a chronic state of oxidative stress, we have an imbalance. We have more electron scavengers than we do electron donors. We've lost the ability to regenerate these. So we can never fix the underlying problem, and it just exacerbates the condition. So these systems are in place for a reason. And again, it goes back to the concept that the body is much smarter than we are. We just got to give the body what it needs, get out of its way, and let it do its job.
Yeah. Yeah, it's hard. Get out of our own way sometimes.
But again, I think it comes back to the fundamental basis of, looking at things like whether it's glutathione reductase, glutathione peroxidase. Most of these, they're metalloproteins, and the metal is usually some trace mineral, whether it's chromium, selenium, or iron. And if you can't make stomach acid, you can't absorb these micronutrients from the diet, so we become seleno deficient. We become deficient in iron or chromium, and then we leads to a dysregulation of glucose uptake and insulin signaling, develop metabolic disease.
Right. Just quickly, because there's other topics I want to get onto, but you've mentioned deficiencies of key nutrients and minerals. From a biochemist standpoint, are you in favor of just doing simple serum testing, or are there other types of tests that might be more revealing, like intracellular levels?
Well, we have to go where the technology is, and I think you can look. Sampling blood is obviously what's extracellular, right? What we sample in the blood, and most labs are done through blood draws.
Yeah.
So what's circulating in our body isn't reflective most of the time in what's intracellular, and intracellular concentrations are what dictate cellular activity and metabolism. So there's a disconnect. And then 10, 15 years ago, we started doing salivary samples, because salivary has been shown, or it's thought, that more accurately reflects intracellular concentrations, because it's secreted by our salivary glands, and there's cells in the salivary gland. So, but I think we have to, and to me, you can test, but then the problem with medicine today is you're treating the numbers. You're not treating the patient.
Yeah.
Well, I think what we have to do, and I'm a fan of testing, but, we know enough now that we can make some assumptions in the general population, right? And this is done even through, I don't believe a lot of governmental research, but they don't tell us the truth all the time, but even the NHANES study, the National Health, that looks at kind of nutrient deficiency. Even the own government, U.S. government, reports that 75% of Americans are deficient in magnesium, 95% are deficient in iodine, greater than 50% are deficient in things like selenium and chromium and other trace minerals and nutrients. So if you just replete and supplement these basic nutrients, macronutrients and micronutrients, then we know we give the body what it needs. Whether you're deficient or not, it's self-regulating.
Yeah.
And then you pee or poop it out. Body this is what it needs, and it excretes the rest.
Yeah.
And some of this is so, cost effective that, I supplement, but also do, testing. I do micronutrient testing. I do an array of tests just to make sure that my body has what it needs, and I can give the body, if it's missing something, then I basically replete it and restore its function.
Which labs do you like to use for that kind of testing?
I think SpectraCell is a good lab for micronutrient testing. and it's a pretty broad array of micronutrients. So I usually do like them. It's not saying there's others, but that's the one I typically use.
Yeah. Yeah. And I completely hear what you were saying about not treating the numbers, treating the patient. And I'll just tell you this story real quickly. I remember teaching a seminar somewhere. I can't remember which state it was, probably about 7-8 years ago. And we were talking about this very topic. And I just shared with all the practitioners there in the class. I'm like, I'm not a huge fan of tests like SpectraCell because, just even if you have a lot of micronutrient deficiencies, what is that telling you? Like if all you do is just throw supplements at people and you think your job is done, your job is not done. And I said, so I look at in micronutrient testing like that as kind of maybe a tier 2, tier 3 type test. There's other things that might be more important for me to use diagnostics for. And I had the young lady come up to me on a break she was a nutritionist or a dietitian, PhD. And, she was like shocked. She's like, I do this test on all of my patients. And I said, well, let me ask you this. How often do you run a SpectraCell test, give them what they need, follow-up test, and all the numbers look good, and you fixed every problem that person has? And she looked at me like with deer in the headlights. She's like never. I'm like, right.
Never.
So it's a necessary part of physiology, and I understand where it kind of fits. But like you said, you got to treat the person and not just the numbers. That alone sometimes is insufficient. So yeah. So thank you for the input on that. Let's talk about perfusion.
Yeah.
Right. Yeah. And in my notes to you, I said, we use this term in our field all the time, but perfusion is king. Like if you can't get blood flow to your tissues, you're behind the 8 ball from the get-go. And well, let me say this first, that in a lot of the lectures, in fact, I'm getting to fly to Minnesota in a week and a half, 2 weeks, to teach a course on functional blood chemistry analysis, just like an introductory course on things like anemias and dysglycemias and this kind of stuff. And we start out with looking at a CBC and helping docs get really good at picking up on things like anemias and looking at ferritin or iron levels and B12 status, because we know that if someone is an anemic person, they are not going to get better until we fix that.
Right.
What kind of shocked me is when I was reading one of your papers and listening to some of your lectures last year, what shocked me was the role of nitric oxide in cell respiration. And to be honest, it was revelatory to me. It was completely revelatory. So I'm not, instead of me just keep talking, I'm going to throw it over to you. Can you describe for us what is the relationship between nitric oxide, hemoglobin, and oxygen? And why is it important that when I'm teaching, for example, which I will be in a couple of weeks on this topic, why should I include nitric oxide in my discussion of looking at a CBC and evaluating someone's tissue oxygenation potential? Because this is huge.
Yeah. No, it's the basis of chronic disease. You made a good point, because every single chronic disease, whether it's vascular dementia, Alzheimer's, heart disease, kidney disease, liver disease, the problem is there's decreased blood flow to that organ. So when you can't get oxygen and nutrients to that organ, the cells in that organ can't function. And then it leads to organ dysfunction, end organ disease, and death. So we have to be able to perfuse the organ and the tissue. But it's not just perfusion. So there's two aspects of perfusion. There's vasodilation, so that we can get more volume of blood to the cells and the tissues. But how do we oxygenate? And that's the role of hemoglobin. So it's the red blood cell, the hemoglobin in the red blood cell. It's actually the mechanism for tissue oxygenation and cellular oxygenation. And this whole process is dependent upon nitric oxide being produced, binding to a cysteine residue of hemoglobin. So now when hemoglobin goes through the capillaries, from the arteries to the vein, and this is known as the Bohr effect in biochemistry, that hemoglobin undergoes a shift in structure, a change in structure, color from the R to the T, the relaxed to the tense state. And it's during that allosteric transition in the capillaries that oxygen comes off. We pick up carbon dioxide, we take it back to the lungs, and we exhale the CO2, we pick up oxygen, then we deliver it. So that's been known for hundreds of years, right?
Yeah.
The regulation of this is dependent upon nitric oxide being bound to a cysteine residue. If we can't make nitric oxide, we lose the signaling aspects of nitric oxide or hemoglobin. So we may be able to oxygenate, but oxygen will not come off in the tissue. So if you look at blood oxygen,
I'm sorry, that just blows my mind.
Yeah. So here's the problem. If you look at blood oxygen saturation, your blood could be fully saturated, 98, 99%, but the cells and the tissues in the organ could be hypoxic because oxygen does not come off the hemoglobin without nitric oxide being present. And we saw this during COVID, right? The problem with COVID was the hypoxemia and the loss of blood oxygen saturation. So it wasn't the problem of oxygen availability, because the air we breathe is 21% oxygen. We only use about 6% of the oxygen that we breathe in. It was the delivery of oxygen. So when your blood oxygen saturation gets low, number one, you're not saturated, but number two, you can't even deliver what oxygen you have to the tissue, and that's why so many people died. So when we were giving our nitric oxide drug in our phase of the clinical trial, we could take hypoxic patients with a blood oxygen saturation of 78, and within 8 minutes of giving our nitric oxide drug, we could bring their blood oxygen saturation up to 96 within 8 minutes, just breathing room air. So no need to give supplemental oxygen, certainly no need to put them on mechanical vents, because that's what killed people. So this really showed me and opened my eyes. We've known this now for 7 or 8 years, but clinically to see this, that if you just give nitric oxide, you improve oxygen saturation, but more importantly, you improve oxygen delivery. Mechanistically, you need nitric oxide bound to hemoglobin to fully oxygenate individual organs, tissues, and cells of the body. And it's really that simple.
It's simple, but it's crazy. And I mean, to me, it's a revolutionary concept that adds a potent branch to clinical models that we've been promoting and talking about.
That's right.
Well, I've been doing it for 15 years now.
Yeah.
So it seems to me that there's a situation like, let's say you're using your finger monitor looking at your SpO2, and it's just because it's 98% doesn't mean that your tissues are perfused.
That's
In the absence of known or probable lung pathology or dysfunction, could we assume that somebody who has a lower oxygen saturation rate is going to be nitric oxide deficient?
absolutely. The lungs are unique in the fact that every other tissue in the body, when it becomes hypoxic, meaning that there's decreased oxygen, every other tissue in the body, there's other mechanisms that lead to vasodilation. Because if you're hypoxic, thing is, I need more blood flow, I need more oxygen, so I need to dilate the blood vessels that hold it. The lung is completely opposite. So we get, you're familiar with this term, it's called hypoxic pulmonary vasoconstriction.
Yep.
So the lung, when it doesn't get enough oxygen, it shuts down blood supply to that part of the lung. Because, and naturally it makes sense, because we only want to perfuse the areas of the lungs that are well ventilated, or we only want to provide air to areas of the lungs that are well perfused so we can oxygenate the blood,
right,
and then deliver that oxygen to the tissue. So if there are parts of the lung that aren't perfused, or that we're not getting good air, whether it's, emphysema or pneumonia, any type of respiratory issue, then the hypoxia leads to pulmonary vasoconstriction. So now we're shutting down blood supply to that part of the lung. And now we only have part of the lungs oxygenating the blood. And so we have to restore what's called ventilation to perfusion ratio. We need to open up the blood supply to the lungs. So now we can basically oxygenate all parts of the perfusion of the lung that leads to better oxygenation. But we have to give nitric oxide in that respect, right? Because only to dilate the pulmonary arteries, we have to give nitric oxide. That's why inhaled nitric oxide is so important. It saved millions of lives of premature babies that have underdeveloped lungs.
right.
And inhaled nitric oxide matches ventilation to perfusion, overcomes the hypoxia, the cyanosis, and it completely corrects the underlying condition.
So for someone who's not in the hospital, not in an ICU setting, critical care, a lot of practitioners that do functional medicine are using, fingertip monitors looking at SpO2. What percentage sat rate do you think, if we see this number, we should be thinking, nitric oxide's probably deficient?
Well, I think when you start to get below, 98, 97% oxygenation by pulse oximeter, then you start to realize there's a problem with oxygenation.
Yeah.
And that's just the oxygenation side. We're not even addressing the delivery, the tissue oxygenation.
Yeah.
So I think we have to, understand this. But here's the other thing we learned in COVID. There were a lot of people who had silent hypoxemia that had blood oxygen saturation of, 85, 90, even sometimes low 80s. But yet they obviously felt awful, but it wasn't critical. It wasn't, dire. But yet at early COVID, they started to ventilate patients that had blood oxygen saturation that fell below 90. Now looking back, we know that was a very bad idea, because that led to the unnecessary deaths, tens of thousands of patients. And two, we know that giving 100% oxygen didn't improve them. Putting them on mechanical vent didn't improve them. In fact, it made them worse, leading to the acidosis and the dysregulation of tissue oxygenation. So if we just give nitric oxide, we can improve blood oxygen saturation, but more importantly, we can improve the delivery of that oxygen in the periphery.
Do oral strategies like your lozenges or the beetroot powder, do they perform adequately enough that they could be used in critical care?
Now, absolutely. I mean, because what we do is we generate nitric oxide gas. If your body can't make it, we do it for you. So the beauty of that lozenge is, you put it in your mouth, it dissolves over 5 to 6 minutes, but we can detect about 20 to 30 parts per million nitric oxide gas. So if you go to the ICU as a premature baby with pulmonary hypertension, or even undergoing cardiopulmonary bypass, they give you 20, 30, 40 parts per million nitric oxide gas inhaled through a nasal cannula. So we deliver that same amount of therapeutic nitric oxide gas through that lozenge. So what we tell people with pulmonary issues is you put the lozenge in your mouth and then you breathe deeply. So now we're delivering that gas that's being produced in the oral cavity through the nasopharynx, delivering it directly to the pulmonary arteries. We do the pulmonary vasodilation. We match up perfusion to ventilation, and people get better.
So what kind of frequency do they have to use the tablets?
Well, everybody's different. In our FDA drug trial during COVID, we were using one lozenge every 12 hours. This was a 30-day study. And we found that, our strategy, our clinical strategy in the drug trial was within 3 days of being diagnosed or onset of symptoms, we wanted to implement therapy. It was an early therapeutic regimen because I think there becomes a process in every disease where you reach a point of no return.
Yeah.
If we started trying to intervene in these patients where they're already, chronically hypoxic on 100% oxygen or even on a vent, then, we probably missed this critical time frame. But even in that drug trial, if we started one lozenge twice a day, every 12 hours, patients got better. We improved blood oxygen saturation by 14%. We reduced the onset of symptoms, the time of symptomology. So people were getting better. We were conducting a clinical trial at a time where there was no focus on early therapeutics. We were having vaccines and mRNA therapy pushed down our throat, and the government wasn't interested in early therapeutics. They were interested in getting this mRNA genetic manipulation in the arms of everybody around.
Amazing. Amazing. Let's move on to another clinical topic, and that is nitric oxide and insulin resistance metabolic syndrome. Right. And I know that there's the obvious link of metabolic syndrome and endothelial dysfunction and cardiovascular risk and events. But I don't know the details, which is why you're here. But I know that there's a relationship between I keep saying glutathione, nitric oxide and insulin in terms of some kind of a regulatory relationship.
Yep.
But I'm also interested in, and we'll start with insulin, but I'm also interested in whether nitric oxide has impacts on things like glucagon, gluconeogenesis, glycogenolysis. So kind of like stepping back and trying to see the big picture of just glycemic states and where does nitric oxide fit? So let's start with insulin. What's the relationship between the two?
So it all starts with insulin. Insulin is an inflammatory molecule, so we need an acute insulin secretion, and then you need to shut down insulin because we know that hyperinsulinemia, chronically elevated insulin levels, is what leads to chronic inflammation.
Yeah.
Well, we now know that insulin signals, right? It's how cells in the body communicate with one another. So when our body senses we have an elevation of blood sugar, then that tells the pancreas, I need to secrete more insulin, because insulin then binds to the insulin receptors, starts an intracellular signaling cascade, and through a number of what's called protein kinases, it activates other cell signaling events. And so one of those, and it converges on nitric oxide synthase in the cell. So when insulin binds to the insulin receptor, it leads to phosphorylation of certain tyrosine residues on enos. That enzyme is functional, makes nitric oxide. Then nitric oxide is what leads to GLUT4 translocation and glucose uptake.
But let me just pause you because I had a question about that. So that nitrosylation of GLUT4 is insulin dependent?
No, not necessarily. So it's depending upon. So there's two. So AMP kinase, very important metabolic switch in all cells. In fact, it's the target of metformin. So if you have a diabetic patient who's taken metformin, the clinical data show that in some patients you get pretty good management of blood sugar. Other patients, not so much. You got to continue to increase their metformin or glucophage. So this works because it targets metformin. It tells or AMP kinase, then AMP kinase turns on nitric oxide synthase production. But again, if that enzyme is uncoupled and dysfunctional, then that's where the signal is. So we don't get nitric oxide produced in the cell. GLUT4 doesn't get post-translationally modified. It doesn't get the signal to go to the membrane and bind glucose. So now you have hyperglycemia, tells the body, hey, I need more insulin, send me some more insulin, but yet the insulin isn't working. And that's the mechanistic basis for insulin-resistant type 2 diabetes. It's a nitric oxide deficiency. In our 2009 paper, we showed that if we could restore nitric oxide production, you could potentiate insulin signaling, could enhance GLUT4 translocation, improve glucose uptake, improve fasting glucose levels, and downregulate insulin. I mean, so insulin signaling and insulin resistance is really a symptom of nitric oxide deficiency. We have to complete the signaling cascade in order to clear glucose from the circulation and thereby downregulating the secretion of insulin.
And that's a new dimension to understanding what insulin resistance actually is. Like, we tend to have surface level discussions. Well, the insulin receptor stops working, but we never really say, well, why is that? Right.
Yep.
So you're saying that nitric oxide is the pivotal player in that. Is the presence of adequate nitric oxide or NOS activation also why exercise can induce GLUT4 translocation to the cell membrane in the absence of insulin, because you drive eNOS production and nitric oxide goes? Is that the mechanism why exercise is so good in that respect?
That's right. So in people who exercise are in good shape, the eNOS enzyme is coupled and functional. So now when we activate it or stimulate it, whether it's insulin or whether it's through exercise and the increase in shear stress and lining the blood vessel, that tells the cell to make nitric oxide. If it can, then it leads to GLUT4 translocation, glucose uptake. And that's why exercise, it's a stimulator or activator of nitric oxide. Right. It's all dependent upon the function of the NOS enzyme. So we have to make sure that the NOS enzyme works so that when it's activated or stimulated, it does its job. And then thereby the cell can do its job and it can signal. Yeah,
it makes total sense, makes complete sense. So what about aspects of glycemic control like gluconeogenesis and glycogenolysis? Is there a relationship between nitric oxide and those, hepatic as well as skeletal muscle functions?
Well, that's less well understood in terms of mechanistic, but I think it goes back to its regulation, right? It's how it senses. So primarily this occurs in fat cells, liver cells, and skeletal muscle, right? Those are kind of our glycemic control target. So if we have decreased blood flow to the liver, then the liver is not sampling, really getting a good sample of what's going on in the body, right? So it can't respond. It's a poor sample. Same thing if our skeletal muscles are poorly perfused because we can't make nitric oxide, then the skeletal muscles aren't getting a good sample, a representative sample to respond. The same thing with adipose tissue. So we have to be able to get an accurate sample that the tissues and the cells can sense and then tell the body to respond appropriately. So I think it's indirectly, it's controlled by nitric oxide, but it's all controlled by how well perfused that organ is. And it's all endocrine glands. And you can go up to the HPA axis, the hypothalamus and the pituitary. If those endocrine cells or tissue aren't being well perfused, not getting an accurate representation of the sampling, so the body can't respond with a normal response. So for me, it goes back to the fundamental basis of everything in physiology, because the hip bone's connected to the knee bone, the heart. And the connection is through the cardiovascular system. So if we can't perfuse and regulate the control of blood flow in every organ, tissue, and cell of the body, then we're not getting a good sample, and then the body can't respond.
Right. So is it the case then that if, for example, I'm not perfusing my skeletal muscle and I'm not getting adequate sampling, am I going to then start generating signals that say increase glucose production because there's a perception at the cellular level? And I know this is happening through hypothalamic sensing neurons, but is there this perception that there's a fuel shortage when in fact there isn't? Is that part of the dysfunction?
Yeah, no, I think that's a fair assessment because again, you're not getting an accurate sample in that particular tissue. Because if it's a dysfunctional tissue, by definition, there's decreased blood flow to that, and that's the basis for the underlying organ dysfunction. So it's not an accurate representation of the sample. So how can the body respond appropriately?
Right.
It's not getting an accurate sample.
Right. Okay. What about glucagon? I mean, obviously there's relationships with insulin. Is there any impact between or interrelationship between nitric oxide, I said it again, nitric oxide and glucagon?
It's one of those things that we really haven't investigated. Okay. But it's metabolic control, right? It's It's fuel. It's a utilization of certain fuel, and every cell type has a preferential fuel. And there's a hierarchy, right? We use sugar primarily, then we break down fats, and then we break down proteins. So it's a hierarchy of fuel utilization. Where in the brain, the heart primarily uses fatty acid, energy source. Brain likes glucose. Other cell types like other substrates. But again, it's the exquisite control and the availability of these substrates and fuel sources that every cell type uses, and it has to be able to regulate it and respond appropriately.
Right. All right, let's move on to vascular health and physiology. Like, the conversation around cardiovascular disease is, it's dominated by LDL cholesterol. And, these days, ApoB is being presented as like the end all be all marker that we should be looking at just to assess somebody's risk. But we know that there are, dozens, if not hundreds, of cardiovascular risk markers or elements. Where does nitric oxide sit? I mean, obviously, we're talking about perfusion and blood pressure and all of these different things. So, where does nitric oxide sit in the spectrum, or let's call it the scale of importance when we're thinking about cardiovascular disease?
I think it's at the top. It's the absolute predictor of cardiovascular disease. Because when you look at cardiovascular disease, what is it? What are the hallmarks of cardiovascular disease? There's decreased blood flow, there's inflammation, oxidative stress, and immune dysfunction. Nitric oxide controls and regulates all of it. Nitric oxide controls, as we talked about, vasodilation and perfusion, but also oxygenation. Nitric oxide decreases inflammation. It prevents the oxidative stress from overexpression of NADPH oxidase, uncoupled mitochondrial electron transport chain, and from an uncoupled NOS. And then it prevents the immune dysfunction. Nitric oxide is really the holy grail in terms of not only a prognostic indicator, but also how, if you fix that, then it fixes every aspect of cardiovascular disease, in fact, all chronic disease. So, but again, it goes back to when you look at biomarker, and that's the problem with biomarker. You have to be able to distinguish, is this a consequence of disease or is it a cause of disease? And most biomarkers that people are using, standard medicine is using today, are consequences of the disease. So targeting those and trying to, the best example is Alzheimer's and the beta amyloid plaque and the tau tangle. These don't cause disease. It's a consequence of disease. So all these drug companies who are trying to target the beta amyloid plaque and the tau tangles, these drugs have failed and they'll continue to fail because it's a consequence of disease. It's not the cause of disease. So I think it's broadly speaking, when you look at cholesterol has no impact on prognostic utility for cardiovascular disease. LDL, HDL ratios, they're meaningless. Now, if you look a little bit deeper and look at number of lipoprotein particle size, oxidation, those have some kind of prognostic utility. But again, are they causing disease? Maybe not. They're a consequence of disease. But certainly if you can decrease the production of those, then we know upstream we're actually fixing some fundamental issues. So I'm not saying that you can't target a consequential biomarker in disease, but you just have to understand this is the consequence of the disease, not the cause of the disease.
Do we have direct studies that look at nitric oxide capacity and rates of progression or regression of plaque deposits or the vulnerability of plaque?
Yes. And so we published a paper maybe in 2012 or 13 where we took patients with kind of asymptomatic plaque. And these are through a carotid intima media thickness. You can take an ultrasound and look at how thick the intima is. So that's the part of the blood vessel that's just below the endothelial cells. And it's intima thickness that occurs in cardiovascular disease. So you get the plaque starting to develop in the lining of the blood vessel. Over time, that plaque grows, and then it'll lead to stenosis, which is an occlusion of the blood vessel. So the issue is cardiologists and most clinicians will look at the degree of stenosis in the artery. And it's not the degree of stenosis or obstruction, it's the stability or the vulnerability of the plaque in the endothelium. So what we did several years ago is we took asymptomatic patients who had kind of a little bit of asymptomatic stenosis of the carotid arteries. We put them on the nitric oxide lozenge for 6 months, and we saw 11% plaque regression. And really the only metric that we could compare that to was aggressive statin therapy, where now people want to get your cholesterol below 200 and really treat that way. But even if you did that, with the most aggressive statin therapy, the best you get is about 2.7% plaque regression after 3 years.
Did you say 2.7?
2.7. If you look at the meta-analysis of all the studies shown with aggressive statin therapy, you get 2.7% plaque regression after 3 years. Yep. Just giving our nitric oxide lozenge, you see 11% plaque regression after 6 months. and we're not getting cholesterol in the basement. We're not making people vitamin D deficient. We're not inhibiting their testosterone or estrogen production. So it's a very viable strategy. The other thing in the literature, and this was from the 1980s, nitric oxide actually stabilizes plaque. So even if you have plaque in the lining of the blood vessels, if you can restore nitric oxide production, you prevent additional plaque activation and stabilize existing unstable plaque, and it leads to the prevention of heart attack and stroke. So again, it's not the degree of stenosis. 50% of people who have fatal MIs have less than 10% stenosis of the coronary arteries. But yet the plaque that's in that coronary artery is unstable. It ruptures and leads to heart attack. So we have to stabilize the plaque. It's not the degree of stenosis. It's the stability of the plaque, which is stabilized by nitric oxide.
So then in terms of biomarkers, would you as a biochemist favor looking at things like myeloperoxidase or the PLA2 test?
Yeah, so these markers show up in an unstable plaque. And it's a reflection of the inflammation, oxidative stress, and the immune dysfunction that occurs in vascular disease. So there's a hierarchy, and you've seen this, where early stages you start to see certain biomarkers show up. Usually the first one is C-reactive protein, acute phase marker of inflammation. And if not corrected and you start to get, plaque deposition, plaque instability, you'll see myeloperoxidase start to show up, and then troponin. And those, once that's released, it's diagnostic for a heart attack. Now you're in acute MI.
Yeah. So, and let's just reiterate a couple of things there, because you threw out some numbers like 11% plaque regression. So I'm just trying to think in terms of vascular flow dynamics. What does that translate into because we're looking at a pipe with a fixed diameter, and you've got stuff around the inside plugging it up, for lack of a better way of saying it. If you reduce the thickness of that, I mean, you're significantly increasing the patency of the aperture for flow. So what does an 11% reduction translate into increased blood flow?
It's about a 30% increase in blood flow.
Almost like a 3-to-1, something like that?
No, that's right. So if you look at laws of hemodynamics, and there's a mathematical model for this. So if you so the degree of vasodilation translates into a fourth power degree in blood flow. So a 13% increase, or let's say a 10 to 12% increase in blood vessel diameter translates into about a 35% increase in blood flow. So it's to the fourth power. So you don't have to vasodilate that much to see an increase in perfusion. So 11% plaque regression and 11% degree of opening of that blood vessel improves blood flow and perfusion by greater than 30%.
That's amazing. It is. I mean, but it's simple math, right? That's all it is. So one aspect is improved patency and blood flow. The second aspect, and I'm seeing three things. The second aspect is changes in plaque stability, right? So vulnerable, immature, inflamed plaque becomes more. Is there a connection between then someone who has a plaque process that leads to calcification and stability that we might pick up, say, on a calcium heart scan? Like, are the people who are able to stabilize plaque turn it into the calcified, old, safer stuff? Can we assume, especially if that calcium heart score is not progressing year after year, that they've got adequate nitric oxide? And to flip that around, if someone has an unfavorable calcium heart score for age and gender, and that is getting worse year after year, can we assume nitric oxide is part of the problem?
Sure, and we have clinical data on that.
Nice.
So, and that's why a coronary CT and a calcium has very little prognostic utility in terms of predicting future events, right? Because if you have calcified plaque, and that plaque is stable, there's very little risk of it rupturing and causing an MI. So I think these are useful in terms of getting baseline numbers and then monitoring your progress. But again, it has no predictive utility for future MI or heart attack events. In fact, it's probably a protective mechanism. You want that hard plaque, and what you don't want is the soft, vulnerable plaque that's at risk of rupturing and occluding the coronary arteries or the cerebral arteries and causing heart attack and stroke. That's the worst thing you want. If you've got plaque, you want to make damn sure that it's stabilized and not at risk of rupture.
Do we have any studies that look at the reduction in calcium heart scores using nitric oxide?
We do anecdotal. We have a number of cardiologists and clinicians around the world that use our nitric oxide technology. And then they just use their best medical judgment. Obviously, what we have on the market now is not intended to treat, prevent, or cure any disease, but we arm the physicians with tools and clinicians you if you use your best medical judgment on what's best for that patient.
Yeah.
I've had enough of cardiologists that have patients with, an elevated calcium at some with 1,000 or 2,000. They put them on our nitric oxide technology, and 6 months or a year later, they have complete normal coronary calcium. So this is anecdotal. It's not been proven in randomized placebo-controlled clinical trials. But the most important clinical trial there is the N=1.
Yeah. Everything has its place. So let me just tell you my own anecdote. And this was before I met you, and I was using a nitric oxide. It's not actually a nitric oxide product. It's a formula that's designed to manipulate the NOS enzyme system to try to dampen INOS and increase ENOS. I'm not going to name it, but you might be aware of it. And so I was working with a lady. She was an elderly lady, and she had been a client of mine for many years. And, I'd worked with her for a while. She'd disappear for 6 months or a year. Then she'd come back and kind of start over again. And so she came to see me one day for other issues. And she said, oh, by the way, I'm scheduled to have a second carotid procedure done because I'm almost blocked again, which we know happens a lot. And I'm like, okay, so I took a note of it. And as I was putting together her protocol for what her core issues were, I put her on this NOS support formula. I'll just call it that. And just because I was like, yeah, it can't hurt. So a couple of months go by, and she was already pre-scheduled for the surgery. When she went in for her pre-op check, they had to do a repeat ultrasound because she was 1 point away from the threshold where the insurance would pay for the procedure. So the cardiologist, anticipating she would progress, said, we'll schedule the surgery. We'll just, do the pre-op ultrasound, and there you go. So she comes back, she disappeared again. She came back 6 months later, and I said, well, what happened with her carotid surgery? And she said, I didn't have it. I said, well, what happened? And she said, well, let me tell you. I went in and he did the ultrasound to check and make sure we were good to go. And he kept looking at me and looking at the screen and looking at me and looking at the screen. And he said, I don't know what you're doing, but keep doing it because your blockage has gone down, and that never happens. And I'm like, well, that was pretty cool. End of one. And so anyways, I thought that's just kind of an interesting thing. So final thing, and then we can talk about your products, because I want to give you an opportunity to talk more specifically about the evolution, because you've been involved in a couple of different companies that make these products, and you're kind of like on 2.0 these days. I want to revisit what you said in the beginning about literature being misunderstood, nitric oxide being the police officers at a crime being mistaken for those who are perpetuating the crimes. So how is it that we can get that confused? Because the model that I was taught in terms of autoimmunity is that the tissue destruction happens when you get upregulation of Th17 systems and then co-activation of INOS. You get this massive amount in local tissue of nitric oxide being produced, and then you're going to get some collateral damage, right? You're going to get some cytotoxicity. And so you're saying maybe not. So can you be a little bit more clear for me? And I know that you can comment on the nitric oxide. I don't want to put you in like the spot and say, well, can you comment on the autoimmune aspect of this? But how do we sort this out and try to get a proper perspective of what the literature says and the role of nitric oxide? Because part of me is thinking, well, this actually might be beneficial for us.
Yeah. Now, look, I never argue with data. It's the interpretation of the data. So the data are very clear in inflammatory situations that there's a mobilization of immune cells and isolation to the site of infection or the wound, overproduction of nitric oxide. There's always collateral damage, but our body always heals from that, right? And how do we heal? How do we repair and replace dysfunctional tissue and regenerate? Well, that's the role of the stem cells. And the signal that tells our own stem cells to mobilize and differentiate is nitric oxide. So from a chronic inflamed state, and yet we're shutting down endogenous nitric oxide production, the stem cells never get the signal to say, hey, I need to go, there's some damage over here. I need to go replace and repair that damaged tissue. So now we have dysfunctional tissue. We have the collateral damage going on and no way to heal ourselves. So we're constantly wearing ourselves out. There's always collateral damage, but we age because we lose the ability to heal ourselves, repair and replace dysfunctional cells. So that's where the dysregulation occurs. So again, I'm not disputing the fact that nitric oxide is always present in there, but it's the signal that that mobilizes our immune cells, gets it under wrap. Then if we have constitutive nitric oxide production, the stem cells get the signal and goes and repairs and replaces those dysfunctional cells. So that's the basis. But again, it's sensing the environment and then mobilizing the proper response to repair and replace those tissues. And without nitric oxide, you don't get that.
Interesting. So, so going back to that autoregulatory capacity, are there any circumstances where that reflex inhibition fails and we get runaway nitric oxide production? And we get more collateral damage.
We thought that probably 25 years ago, and you brought it up earlier in septicemia or septic patients. So when you get chronic immune response to a systemic infection, 25 years ago, we thought, it's overexpression of iNOS. It's too much nitric oxide production that leads to systemic vasodilation, loss of blood pressure, loss of tissue perfusion, loss of perfusion pressure, end organ failure, and death. So there was a clinical trial 25 years ago where they gave a NOS inhibitor to septic patients. And the rationale was if we could inhibit iNOS production of nitric oxide, can you prevent the loss of pressure, get organs perfused, and prevent death from end organ failure and septicemia? And really surprisingly at the time, the patients who got the NOS inhibitor had higher morbidity and mortality than those who got the. So that told us, well, again, iNOS overproduction of nitric oxide may be a consequence of sepsis, but it's not the cause of end organ disease and end organ failure or death in septic patients. So inhibiting nitric oxide from every clinical perspective that we've known about in the past 40 years seems to be a really bad idea. Now, we still don't understand the exact regulation of what nitric oxide is doing in septic patients, but it's clear from the clinical trials that it's doing it for a reason, and you inhibit it at your own demise.
Very interesting. Yeah. Okay, let's pivot and let's let you talk about your products, and you can talk as much or as little about your, the first evolution of products that you produced. And I know now you've got Bryan Nutraceuticals and a couple of good. I just checked before we hopped online. You're sold out of some stuff.
It's been crazy. Yeah. So now I'm a basic scientist by training, and my whole objective in getting into this field was number one, understand how the human body makes nitric oxide, what goes wrong in people that can't make it, and then if we understood that, then we had really the information that we could develop safe and effective nitric oxide product technologies to really fix the underlying problem.
Right.
So we've done this now in a number of different kind of product categories. And I was part of a drug discovery program at the Institute of Molecular Medicine when I was on faculty at UT Medical School. Our whole motive and drive and motivation was drug discovery. So everything we do in academia is designed to develop safe and effective drugs. Number one, to understand the mechanism of the disease to the extent that we could fix it and develop rational therapies, get to the root cause. So in 2006, 2007, I started filing my own patents because we figured out a way to make nitric oxide. Those patents became issued. University of Texas owns those patents through my employment agreement. And then so I started companies where we license my patents back from the University of Texas, and then we productize or bring these products to market. We did this first in nutrition and dietary supplements because we went and we got some legal opinions on if we could, and a lot of what I did was discovery of nitric oxide through natural product chemistry or natural product technology, utilizing nature's ability to make nitric oxide. So in that case, you really don't need a drug application for that. We can just basically recapitulate nature and provide a source of nitric oxide that the body's used to seeing. So we were able to do that. We brought it to market as a dietary supplement. So the whole basis of everything I've been trying to do for the past 25 years is if your body can't make nitric oxide, then we got to do it for you, right? It's kind of like if your body's low in testosterone, your testes aren't making it, your ovaries aren't making estrogen, then what do? You have to give that molecule. You have to replete that molecule because obviously your body's lost the ability to make it. But the other important consideration was, unlike testosterone, I didn't want to inhibit your body's ability to make nitric oxide to where you get dependent upon my product technology.
Right.
It's a great financial model. These testosterone clinics are making billions of dollars, right?
They're
making you dependent upon your ability to get it from them. But we understand the enzymology and biochemistry of nitric oxide to where we can also recouple the NOS enzyme. We can reestablish the oral microbiome through this technology. So everything I do is if your body can't make nitric oxide, we do it for you. But more importantly, we fix the reason your body can't make nitric oxide. We prevent BH4 oxidation. There's a certain redox potential and electrical voltage needed to prevent the extraction of an electron from BH4. If you prevent BH4 oxidation, you maintain NOS coupling. So we improve endothelial function, and through the development of this orally disintegrating tablet, we're basically improving the diversity of the oral microbiome because we're giving these nitrate reducers, these facultative anaerobes, a substrate to respire on. So now we're fixing both. We're basically improving both production pathways by the technology that we developed. And now my motivation, we've developed a topical nitric oxide. We've got drugs in my drug company, Bryan Therapeutics. We've got drugs going through phase 3 clinical trials for Alzheimer's, ischemic heart disease, got a topical drug for diabetic ulcers. And there's really not a single clinical indication where nitric oxide would not be beneficial. When you understand that nitric oxide at the right dose, at the right time, in the right patient will make everything they're doing better. So that's really the differentiating factor from my product technology. We've done this through several companies now. The first company kind of moved away from the science, was putting my integrity and credibility at risk. So I divorced them several years ago. They still have the license to my product technology from University of Texas, but I've served out my non-competes. And so I've started additional companies to really maintain the integrity of the science. Because to me, that's the most important thing. And you brought up a very, very important point earlier, because now there's dozens or hundreds of companies and nitric oxide products out there, or so-called nitric oxide products. And I get emails and texts and phone calls every day, dozens, if not hundreds, from people who hear our podcast or these interviews and go, you know what, Nathan, I took a nitric oxide product. I saw these nitric oxide chews or gummies on TV. I took it and it didn't do anything for me. So nitric oxide didn't work for me. And I go, no, that's where you're mistaken.
Yeah.
Nitric oxide always works for you if the product generates nitric oxide. So what you're doing is you're buying a product that doesn't generate nitric oxide, that's sold as nitric oxide. And that's very dangerous. That could lead to the complete destruction of a field that I think will change the world and save the world and save healthcare. So now it's become my objective and my motivation. All these companies out. Look, you can sell products. There's a lot of products out there that contain really good ingredients that people can benefit from, but they don't do anything with nitric oxide. So it's not to say that they don't work. They work on other pathways. People can get better by affecting pathways that may be completely independent of nitric oxide. But just don't put to market a product that deliberately know cannot generate nitric oxide and call it a nitric oxide.
I think I've seen you. Yeah, I'm sorry to cut you off, but I'm pretty sure I saw you in one of your lectures bring out, I call it your magic sniffing wand.
Yeah.
So tell people about that. What do you prove with that?
Well, we prove that we generate nitric oxide gas, right? So we have a gas phase nitric oxide analyzer. Maybe if we go back to an hour and 45 minutes ago, nitric oxide is a gas when it's produced in the body, and then it's gone in less than a second. So it's really impossible to detect nitric oxide production in an intact human. We can do it in animals and animal models. But in terms of product technology, there's certain ways you can determine if a product actually produces nitric oxide. So you can give precursors or substrates. You can look at, in vitro cell culture models and see how it produces nitric oxide. For what we do, which is different than anything on the market and that even on the planet, is our products actually generate nitric oxide gas. And we can verify it, we can quantify it, and we can detect it. So I get people asking me about, well, I've taken this product. And I say, well, send it to me. Let me do a demonstration. And I'll show you that this product, number one, biochemically, there's no way in hell it can ever generate nitric oxide. But at least empirically, I can show you that it doesn't. So people send me these products. We put it in water. I'll put it in my mouth. I'll take it. And then we'll detect if any nitric oxide's coming up. And so my products generate nitric oxide. If they don't, I don't bring them to market. And everybody else's product hopes your body can convert it to nitric oxide. As we discussed, the problem is the reason you're nitric oxide deficient is you cannot convert these precursors or substrates in many of these products into nitric oxide. So it's useless. And I think that's what we have to do to maintain the integrity of the science and really call out these deceptive, fraudulent companies who are out there spending millions of dollars a month trying to ride the wave of nitric oxide and selling a deceptive product that doesn't work. I'm going to call them out. I'm going to prove it.
So talk to me about, you have a lozenge and you have a beetroot powder. Talk about the different practical uses of those things. And I'll make sure that we put links to your website where people can go and get this stuff for themselves or for the patients. So what's the difference in the applications of the lozenge versus the powder?
Well, again, it goes back to the simple fact that nitric oxide is a gas, right? I'm still the first and only person in the world who's ever made a solid dose form of nitric oxide gas. That was the basis of the lozenge. So the lozenge is designed we create this matrix. there's really a lot of intricate design in there. So we have to create a matrix that when it's put in your mouth, this matrix slowly falls apart. And then we start to generate nitric oxide gas at a very specified rate over a very specified period of time. So the lozenge I designed to have a resident time of about 5 to 6 minutes, depending upon how active you are for this. But as soon as you put it in your mouth and it hits your saliva, we generate nitric oxide gas. We can detect it with our nitric oxide analyzer. It's vasoactive. So if we use an ultrasound, we can see dilation of the cartilage within about 12 to 15 seconds. So we produce nitric oxide. We can demonstrate the vasodilatory effects of it. And then now when we swallow our saliva for the next 4, 5, 6, 8 hours, we're getting another burst of nitric oxide gas. So that's number one. So that's kind of our foundational nitric oxide daily support. Your body can make nitric oxide. We do it for you, but we improve your body's ability to make it. So theoretically, you need less and less of my product over time.
Yeah.
If you live in utopia, right, where you're not exposed to toxic. And then, in 2012, beets became the hero vegetable from the 2012 Olympic Games in London. It was realized that these athletes were taking beetroot juice, improving their performance because of a nitric oxide effect. So I started measuring these beetroot products, and 99% of the beetroots on the market didn't do anything. They didn't have any nitrate, no nitrite, no nitric oxide activity whatsoever. So now I create a fermented beet powder. So again, we ferment the beets, we concentrate it in nitric oxide activity. And then when you put this in water, so we develop this as a powder that you reconstitute in 2 to 3 ounces of water. And as soon as it hits solution, we generate nitric oxide gas. So you put this in water, you mix it really quickly, and then you take it as a shot. It's not meant to be sipped on or consumed throughout the day because it's generating NO gas and you're losing it in the headspace. Pour it in there, mix it, take it as a shot. And then we have a topical nitric oxide that I first developed for healing one of my dad's non-healing wounds. My dad's a paraplegic from a car accident in '84. He's just turned 75, so I've been treating decubitus ulcers for 30 years.
Wow.
We actually healed a non-healing wound, and we've done this dozens of times with a topical nitric oxide. So I brought to market a topical nitric oxide for skincare because the skin's an organ too, right? Like the heart, the brain, or the sex organ.
Sure.
Without sufficient blood supply and perfusion, it fails. So we make a topical nitric oxide that when you apply it to the skin, generates nitric oxide gas. Again, we can quantify it, we can detect it, we can verify it, and it perfuses the skin. We've got 5 published clinical trials on that product, complete transformative results in terms of skin care and beauty, tone, texture, and clarity of the skin improve. We got studies on acne, scar remediation, wound healing, an incredible, it's a new category in skincare. So those are our core products. And as I mentioned, I've got a drug company where we're taking this core technology through FDA. So now that we can actually penetrate the so-called standard of care in allopathic physicians, that hopefully in the next year or two, we'll have drugs that they can actually write a prescription for, and they replete nitric oxide. And now for the first time in Western medicine, it can actually start getting better.
That's crazy.
But yeah, you can't. So let me make a point. You
Yes.
can't get nitric oxide in a capsule. You cannot, by any stretch of the imagination, get nitric oxide in some gummy or chew or hydration or product. Nitric oxide's a gas. It has to be deliberately controlled and produced through some very unique technology. And we're the only people in the world who do that.
So the powder that you're referencing, the beets with the Z, so that's designed to generate nitric oxide that then you swallow
That's
rather than delivering nitrites, nitrates to your microbiome and having the bacteria do the work.
That's right. So everything we do is not dependent upon the oral bacterium, and it's not dependent upon stomach acid. Because if that were the case, everybody that took it would have a differential response, right? So that's what makes us different. We deliver the same amount of nitric oxide in every single person that takes it, whether you use mouthwash, whether you're on an antacid, whether you have the right oral bacterium. So we pre-convert it. That's through fermentation. The other important thing we do is that oxalates are a problem. The people who are prone to kidney stones or things like that, oxalates and oxalic acid are a problem. So in our NO beets powder, we remove the oxalates, we remove the beet taste, the beet color, the beet pulp. So now we can make a beet product. It's not only efficacious in terms of its ability to generate nitric oxide, but we made it a mixed berry flavor. Great tasting. Put electrolytes in there to improve cellular hydration. Then we add mitochondrial ATP for energy. So we position that product as a pre-workout to help performance. Also as an energy drink. We got billions of dollars spent on 5-hour energy, Red Bull, Monster energy drinks that are killing young kids, stimulant-ridden, So we want to offer a safe energy alternative, get natural energy to increase blood flow, mitochondrial function. It's actually good for us. And that's what we hope to do to replace things like 5-hour energy in Red Bull.
Right. So since you're delivering nitric oxide directly, can I surmise that there would be clinical applications for things like periodontal disease, esophagitis, gastritis? Like, first site of contact is going to be your mouth, your esophagus, and your stomach.
Yeah. So what we're trying to work on now, so to answer your question, we just don't know. We think, but we don't know. But before we do anything, we put it to the test and verify and validate. So here's what we know today, that in periodontal disease and gingivitis and really in dental medicine, we can't just put an atomic bomb in the mouth like an aseptic and an antiseptic mouthwash, because you're killing the bad guys, sure, but you're also killing the good guys.
Right.
Believe the commercials you hear when you talk about Listerine and Scope killing 99.99% of the bacteria in your mouth. That's not a good thing, by the way. It's damaging. It's causing a lot of collateral damage. So what we're trying to do in working with the dental medical community is, how do we selectively kill the pathogens? Because there are known pathogens in periodontal disease and gingivitis that contribute to disease. How do we selectively kill those, but maintain the integrity and the diversity of the oral microbiome? That's what we're working on now, and I think it'll transform dental medicine and really help dentists get to the root cause of periodontal disease, gingivitis, addressing the oral systemic link, protecting the cardiovascular system, completely restoring the diversity of the oral microbiome.
So is there any danger in delivering nitric oxide directly to the mouth in devastating the oral microbiome, even though you're trying to do good things?
Now, we have data showing that the spirochetes, when they do the probing into the gingival tissue through dark field microscopy, you can look at the communities, the spirochetes, and then we give the lozenge, we retest, completely kill the spirochetes. So what we're trying to do now is, the community of bacteria that live on the gingival tissue is much different than the bacterial communities that live on the dorsal part of the tongue, where the nitrate producers are. So what we try to do is target the gingival tissue with patients who have periodontal disease and gingivitis. The lozenge does it. Again, most infectious pathogenic bacteria are sensitive to nitric oxide. And if you give nitric oxide, you eradicate those bad guys. In fact, they proliferate because the body's lost the ability to make nitric oxide. So now they're in an environment where there's no danger. We give nitric oxide, the immune system takes care of itself, and they're sensitive to it. And then we're also finding, through additional testing, that the lozenge, because we crack it in the mouth, we're actually improving the diversity of the oral microbiome. Yes. So now the next challenge is, how do we verify that we're selectively killing the bad guys while maintaining the good guys? And if that's the case, then really that's the holy grail, not just in cardiovascular medicine, it's the holy grail in dental medicine.
Yeah. You said in the grand design of the body, referencing a different topic, I would imagine that probiotic species probably are more nitric oxide resistant.
No, that's right. So these, and probiotics are important, but I haven't found any oral probiotic that's addressing the bacteria that we're most interested in, that are responsible for nitric oxide production and the regulation of systemic blood pressure. And most probiotics are designed to affect the gut microbiome.
Yep.
And look, they're important. Microbiome in the distal gut is much different than the microbiome that's in the oral cavity, right? By design. So we have to selectively start to regulate and change the communities.
So you wouldn't want necessarily to take a probiotic capsule or powder that's designed for your gut and just stick it on your tongue and roll around your mouth for a while.
No, probably not. I mean, the communities in the distal part of the colon are different than what's in the mouth. We have to select those, and it's by design. It's a very rich ecology, and it's a competition for resources. So again, we give the body what it needs. The body responds appropriately and it does its job. Same with the bacteria.
Amen. All right. Where can people find you?
I first send people to my educational website. I do a monthly blog at drnathansbryan.com. Again, I'm not trying to sell you anything. It's just providing accurate information, education, so that not just consumers can be informed and make educated decisions on products, but also physicians and clinicians become informed on how best use their best medical judgment to effectively treat their patient. So that's first. I'm on social media, Dr. Nathan S. Bryan on Instagram, LinkedIn, Dr. Nitric at Twitter. And then for those of you interested in product technology, it's n101.com.
I like that one.
Topicals are found, our supplements, our powders. And then if you want to keep track of our drug discovery program, go to bryantherapeutics.com. Again, we're taking this technology through FDA clinical trials, and our objective is to get safe and effective nitric oxide drugs around or on the market so physicians can use this in their patients.
Will you have someone on your end shoot me all those links that I can keep them, put them in the episode description?
Absolutely.
That'd be perfect.
And if you want a code, Steve, we can give you a code, and then that way we can
Yep.
enough get code. Yeah.
Yep, that'll be, you just let me know how much and how long it's valid for, and we'll probably put this episode up in a week from today.
Okay. Yeah,
That's good. You've
do a
been-
follow-up email now.
That's perfect. You've been so generous with your time. I can't thank you enough. I truly appreciate it. And this has been, one of the better interviews that I've done.
Well, thank you, Steve. Hope to meet you in person soon.
Yes, absolutely. Next time I'm in Austin, we have to do that.
For sure. We'll get together with Tom.
Yes, perfect. All right, Dr. Nathan Bryan, thank you, sir. I appreciate it.
Thank you. Take care.